In general, a gasoline engine achieves maximum efficiency if the combustion pressure in the cylinder reaches maximum when the crank angle is about 10 degrees past top dead center. This means that ignition should be timed accordingly. This graph shows the process in terms of the pressure changes inside the cylinder. Even if ignition takes place at point 1, combustion doesn't start immediately. Instead, combustion starts at point 2, and compression starts to increase. The compression reaches maximum at point 3, and combustion comes to an end at point 4. The period between 1 and 2 is called the ignition delay time. For a given fuel, this delay is more or less fixed, irrespective of the engine speed. So let's think about what happens if the engine speed increases. Because the ignition delay time between 1 and 2 is constant, the angle through which the crank rotates in the same period of time increases. The point at which maximum pressure is reached lags behind 10 degrees. So in this case, it is necessary to advance the ignition timing. If the load on the engine increases, the volume of the air-fuel mixture and the compression pressure inside the cylinder increase. The temperature of the air-fuel mixture goes up, and so the mixture burns faster. As a result, the combustion time gets shorter. This graph shows what happens. In this case, the ignition timing has to be retarded. It is changed according to the engine speed and driving conditions. This is achieved by altering the ignition advance angle, which is controlled by the advancer incorporated in the distributor. Ignition timing is controlled by a governor advancer according to the engine speed and by a vacuum advancer according to the load on the engine. The governor advancer controls the ignition advance angle by rotating the signal rotor slightly relative to the distributor shaft. And the vacuum advancer controls the advance angle by changing the position of the pickup coil. Let's take a closer look. The governor advancer consists of a cam plate, flyweights, and governor springs. The cam plate rotates together with the distributor shaft. Two flyweights rotate on the cam plate with support pins as their centers. At low engine speeds, the flyweights are kept closed by the force of the springs. As the engine speed increases, the flyweights are gradually thrown outward by centrifugal force. Then the cam plate moves the signal rotor in the direction of rotation until the centrifugal force balances the cam spring force. This operation controls the advance angle. This graph shows the relationship between the degree of the advance angle and the engine speed. Next, let's take a look at a vacuum advancer. Here, a diaphragm is connected to the pickup coil with an advancer rod. This diaphragm responds to the vacuum in the intake manifold. When the load on the engine is light, the throttle valve opening is also small, so a vacuum is generated at the diaphragm, pulling the advancer rod moving the signal rotor to the left and advancing ignition timing. When the engine load is heavy, the accelerator pedal is depressed, the throttle valve opens wide, and the vacuum in the intake manifold decreases. Then the spring pulls the diaphragm to the right. As a result, depending on the engine load, the pickup coil moves in the same direction as the signal rotor's rotation, retarding ignition timing. In automobiles, various types of vacuum advancers are used according to engine specifications. This graph shows the relationship between the intake manifold vacuum and the advance angle. The role of the spark plug is to reliably generate strong sparks and thus ignite the air-fuel mixture. The ignition sparks jump between the spark plug's center and earth electrodes. The spark voltage is high or low in proportion to the spark plug gap. Through normal use, the gap will increase, causing the engine to misfire during acceleration. Therefore, the spark plug should be inspected periodically to maintain optimal spark gap. Let's take a look at electronic spark advance, ESA. Instead of a mechanical advancer, an ECU or electronic control unit controls ignition timing in this system. This system senses engine conditions based on signals from various sensors. The ECU determines ignition timing and turns the primary current on and off. As this graph shows, conventional mechanical advancers could only control ignition timing in direct proportion to the engine speed and manifold vacuum. But using sensors and the ECU, ESA can achieve control closer to the ideal for the engine's running conditions. In ESA, the distributor has two integrated pickup coils, one of which generates an engine speed, or NE signal, and the other of which a crank angle reference position, or G signal. While the engine is running, these signals are continually transmitted to the ECU. In case of the D-type EFI engine, other sensors are provided for the ECU, such as the vacuum sensor, throttle position sensor, knock sensor, water temperature sensor, and vehicle speed sensor. Next, let's take a look at a direct ignition system, or DIS. Conventional ESA generated a high voltage with one ignition coil and sent the voltage to each spark plug with the distributor. But a DIS transmits ignition signals to multiple ignition coils and distributes the power from the ignition coil directly to the spark plugs. Let's have a look at a standard ignition system. Unlike a transistorized ignition system, A standard ignition system turns the primary current of the ignition coil on and off mechanically using the distributor's breaker points. The rotation of the cam on the distributor shaft opens and closes the breaker points. This turns the primary current of the ignition coil on and off.